Hello, fellow problem solvers. So today we're going to be talking about invariance. And I've made a video on, and I've solved a couple of problems with invariance, but now I want to focus just on the general concept overall. What is it? How do you do it? And the first really step is, what is invariance? It's really a higher order problem solving technique. It's saying that when you're working on a problem, and you see there's something that's changing in the problem. Say there's some transformation that's happening again and again. It might be happening differently at different times, but there might be something that's the same as it's happening. You might see this in games or whatever, or any sort of like algorithmic changes that are happening. You ask yourself, while this change is happening, what is something that remains constant or something I can really control? And when I say control, what I really mean is something that you can model or evaluate, algebraically evaluate, like a value of something. And say a good example of invariance, actually before we get into the example, like here's a couple of questions that you can ask yourself when you're seeing these changes happening in problems. One of them is, what are all the possible end states? So a state of there's a state that the problem is in before a transformation, then after a transformation, it's in another state, and then another state. And then you might come to a point where you can't do any more transformations. And you ask yourself, well, what does that point look like? What are all the possibilities for that end state? You might also look at periods. Do these transformations create any periods of any sort in the problem? For example, if you're looking at, say, the Fibonacci sequence, you have periods. So this is not invariance or monovariance in a strict sense, but you have periods modulo any natural number, right? And you can actually prove this. But an example with invariance, where you're actually looking at end states, is say a problem where, say n is a positive integer, and you have numbers 1 through 4n plus 2 written on the blackboard. So you have 1, 2, 3, 4, all the way till 4 times n plus 2. And an example is, say you have numbers 1, 2, 3, 4, 5, 6 written on the board. And at every turn, your friend takes two of these numbers and writes their absolute difference on the board. So it takes two numbers, deletes them, and writes their absolute difference on the board. And the problem says, can a 0 be written on the board at the end? Right? And the answer is, well, there's an invariance here happening. So what is something that remains constant while you're writing a minus b? The thing that does remain constant here is, say, if you take 2, if you have 1 and 2, you'll have 1. If you have numbers 1, 2, 3, 4, 5, 6, you take 6 and 4, you have a 2, 2, 1, 3, and 5. You take a 2 and 2, you have a 1, 3, and 5. You take a 5, 3, you have a 1, 2. But something while you're doing this, so you can have a 1 at the end. You can have a 3 at the end. And as you try out different transformations, you may find that, say if you take 5, 4, you get 1, 2, 3, you get 1, 1, 1, you get 1, so you have 1, 6, you can get 1, 3, and 5 on the board. And once you try different stuff out, you see that the only numbers you can get on the board are 1, 3, and 5. If you try, say, n equals 2, and you have numbers 1 through 10 written on the board, you'll see that you can get numbers 1, 3, 5, 7, and 9. I believe you can get all these numbers on the board at the end. And now the question is, why can't you get any of the evens? Now it's sort of hinting at you're not going to be able to get 0 here at all. And the question is, why can't you get any of the evens? And what remains the same is, and this is a common invariance, that parity remains the same. If you delete the numbers a and b, and you write a minus b in absolute values, what you're left with, say if the sum of the numbers before was, of all the numbers aside from a and b, if it was s, then your total sum before you made the move was s plus a plus b. After you make the move, it's s plus a minus b in absolute value terms. Now, a minus b and a plus b have the same parity. You can test it out, you can prove this, they have the same parity. So s plus a plus b and s plus a minus b in absolute value terms have the same parity. Now, given at the beginning that this whole sum is equal to n plus 2 over 4, n plus 2 over, so it's 2n plus 1 times 4n plus 3, if I'm not mistaken, because that's the sum at the beginning, and it's odd. That means at the end, because the parity remains the same, at the end you'll also have an odd sum, which means an odd number. So that's why you can't have a 0 at the end. But this is an example of you looking at, okay, what's my end state? What are all my possible end states? How can I reach them? And then you're looking for different invariants, different things that don't change as the situation, the numbers written on the board, change. So that's invariance in a nutshell. And how you practice this is with every technique. You have this little nugget I gave you. And now go out, try to solve, if you haven't solved the 3 problems I've covered on invariance, please do. I might cover some more in the future. And try to solve them, try to see if you come up with problems, if you see problems which use invariance. Try to see if you come across problems which, when you try to solve them, they have something that's changing. And then with that change, try to figure out, is there something that remains the same? Something I can control? A good example of this is also, say, a game where you have 20 coins on a board, on a table, and 2 players take alternate turns, and at each point you can remove 1, 2, or 3 coins from the table. Who can win? Is basically a question. And this is a bit of a copying, maybe strategy sort of situation as well. But the potential invariant that one of the players can take advantage of is they can always have the sum decrease by 4 after their turn. So that's another cool invariant. And you come across these a lot, but the thing is, solve problems and then you'll get better at this. And most importantly here, that's the basic principle. And this is the basic principle. Now, it gets applied. It can be applied to simple problems like the one I described here, or it can also be applied to very, very difficult problems. I can spoil a problem for you now, and the problem is from the 2021 IMO. A very difficult problem was just an invariance. It was one invariance that if you figured out, you would solve the problem. I covered it on my channel. Or you have also an invariance, even there was a problem that was a 3rd or 6th at the IMO, which used a bit of a complicated monovariance. It looked at something that changes in a controllable manner to come up with something and solve the problem. But this principle can be applied in many situations, and now you're aware of it. And as always, thanks for problem solving.